Yeah, so this is what we want to put, right? So Laplace of y double dot or theta double dot will be this, s square theta s minus s y 0 and s dot 0, right? So we can go back again, conditions to be 0, always assume initial, since we, okay, so basically a ratio of input to output to input. Again, if you have multiple inputs and multiple outputs, there will be, like for example, if you have let's say so if you have m inputs, for example, your y is y1 y2 up till ym, right? So you have m inputs, right? M outputs, and your inputs u is like k inputs u1 to uk. So there will be a transfer function matrix basically. When I say y of s over g of u of s, it will be a matrix gs, which will be how many transfer functions? M into k transfer functions basically, right? So for each input output pair, there will be a transfer function. So it will be g11s g, so for output 1 and input 1, for output 1 and input 2, right? Similarly for output 1 input k, right? So you will have g of, for output m input 1, for output m input k, so there will be m into k transfer functions. So transfer function is for each input output pair, remember that. Okay, so now let's get back to, I think Michael asked a question last time about the initial conditions, right? So we can start with an initial condition and show you that initial conditions can be treated as an input to the system. And I also will come back when we do the state space to transfer function thing. So let me erase this thing for now. So let's say for now, let's not assume that initial conditions are 0, okay? And then we will derive a transfer function for this particular problem, right? So we have a example, a single link robot arm whose differential equation are given by this here, right? And now we want to find a transfer function where y equals to theta, let's say, right? So your output is theta and input is your torque that you're applying to the system, right? So that's the whole thing. So if we take this is the differential equation we have. So we will take Laplace on both sides, like do a Laplace transform on both sides. So if we do that, then it will be m L squared by 3 s square theta, or you can theta s, right? And it was s theta zero, something like that. Let's say this initial condition is not 0 for now, okay? And if we do that, then let me just check one thing before we go there. So this will be multiplied by 0 and theta dot 0, okay, equals to tau of s, so Laplace of this, and then Laplace of b theta will be s theta s minus theta 0, right? So if the initial conditions are not 0, this is what we have, and then now we can segregate them, right? So ml squared by 3 theta s s square theta s, right? So basically separate out terms like things multiplied by theta s. So that will be your ml square by 3 s squared and plus b, this one right here, bs theta or bs, and then you can take everything else this side, it will be ml square. So for now let's ignore this, just want to show you if one initial condition is not 0 then what happens. So ml square by 3 s theta 0, right? So we can separate out theta 0 terms, which is minus plus b, right? So that's your theta 0 term, and then you have tau s, right? So now if you see this, what I'm saying that now if you see we have to find ratio of, so one transfer function will be with respect to theta s and tau s, right? So that transfer function, and then there can be one transfer function with respect to, so there will be two transfer functions here. One will be theta s over tau s, which is the output versus input, which is equal to 1 over ml square by 3 s square plus bs, right? And if you see the other transfer function, or you can keep multiplying this here, just tau s here, plus there will be one with respect to theta 0, so that will be ml square by 3s plus b over this ml square by 3s square plus bs into theta 0. So now you see it's into theta 0 thing. Right? So there are two parts of it. So your output is made up of two linear combinations of transfer functions. So this can be treated as an input. So that means there are two transfer functions, one because of theta 0, what happens to the output, and one because of input, what happens to the output. So that's why generally when we are talking about a transfer function which is a ratio of output versus input, the initial conditions are not considered here. Okay, so that's the goal. Questions here? Anybody have any questions? So simply put your system into S domain by taking Laplace and then find ratios. That is the goal here. Ratio of output versus input. Okay, and initial condition can be one of the inputs. Okay, and you see that the characteristic equation, the denominator is same in both the equations. The only thing that changes is the numerator part. Okay, so if system is stable, what happens? If let's say this system has your poles are in left half, means negative. That means things die down because of initial conditions. And okay, so this is how you can you can say that your response is made up of 0 initial conditions and non-zero initial conditions. So you basically sum them up. Okay, so once you have the transfer function, basically it looks like you can, so MATLAB has that functionality of actually directly putting the transfer function. You can put transfer function and simulate things. Okay. So what do you think the poles here will be if you just do the math here? What will be the poles? Anybody? How do you find poles? Or what are poles? So roots of the denominator, right? So what will be the roots of denominator here? Anybody can find, so s square plus 3b over ml squared, right? Into s equals to 0. You can take s outside. It will be s plus 3b plus ml squared. equals to 0. So one pole is S equals to 0, another pole is equals to minus S equals to minus 3B by L ML squared, right? So simple, like you can always do partial like factorization and then compute the poles here. So one pole is at 0 and other is a negative of minus 3B by ML squared, right? And 0, there is no 0 here like in this equation. And we'll see how poles and zeros affect the behavior or output, but that's we'll do later and maybe in the Monday's class. So let's do an example, a bigger example now that this is the example, this problem you did, you have simulated, right? You have equations of motion. This is what you got when you derived them, and we can put them in state space form, right? What are your states? X is theta dot, phi dot, theta double dot, phi double dot. So those are your, also not double dot. X is theta phi, theta dot, phi dot, and then that is x dot. So these are your 4 states, right? Input is tau. So this is your f of xu. Okay? So this is your nonlinear equation that which you have implemented. And what will be the equilibrium point here? How do you solve for equilibrium points? So yeah, just making this equals to 0 and solve for your state. So basically, you will see that these things don't matter, whatever angle they are, because they can remain constant, right? They can be anything when you start, but they should not change. So this is the solution we get, that your torque should be 0 and your rates should be 0, and your phi and theta can be anything, like whatever the initial conditions are, they stay there basically, right? If your phi, theta e dot and phi e dot are 0. So these are x, these are your x3 and x4, right? So your x1 and x2 can be anything, and there can be multiple solutions, but it means wherever you start is your equilibrium point, as long as things are not moving and there is no input to the system, right? So you don't have to linearize it because it's already a linear system. There is no x1 squared or sine of x1 or those terms. So you can also do a test on here whether it is a linear or not, but it is a linear system, so we don't need to linearize it. So that's good. Again, transfer functions are only defined for linear systems. They are not valid for nonlinear systems. Okay, so we have 2 differential equations. If you solve for if you remember, this is what you got from your Lagrange equations, right? So the output was 2 second order differential equation. So we are moving now. We are we want to find a transfer function here, right? And so what you can do is you can define 2 outputs this time. So y is theta and your phi, basically. So you have a sensor which basically gives you the 2 angles, one for the solar panel and one for the satellite, right? And these are the 2 second order differential equations that you have, and now we want to find transfer functions. So again, there will be how many transfer functions this time? There will be 2 transfer functions because there are 2 outputs and 1 input, so 1 input out. So there will be one will be theta s over tau s, and there will be one will be phi s over tau s. So basically there will be, you have to, and when you are finding transfer functions, you can always consider like for simplification, the other quantity 0 when you are finding transfer function for one quantity. So it will be clear when we, so how do we proceed here? Anybody? What is the next step to do? We have to put this into S domain, or we have to take Laplace on both sides for both the equations. Okay? For both the equations, you take a Laplace with initial condition 0, right? So what will be that? I can, before going to the next page, maybe we can solve it here. So that is the first equation. Laplace on both sides will give me s square theta s. Anybody have a confusion here? Like just when I'm taking Laplace, when initial conditions are 0, it's really simple. Like if there is theta double dot, then Laplace of this is this, s square theta s. So next is b by js. Laplace of theta dot is s theta s. Okay, and Laplace of k by js, this is just theta s, right? Equals to b by js. See this, why this problem is little complicated than a single input single output case, because your terms are correlated. Means your phi is appearing in both equations and theta is also appearing in both equations. So to separate them out, either you have to take a matrix inverse or solve them for them individually, which okay. So that's why this is little complicated than a single input single output case. So we have phi s, s phi s, then k by js, phi s plus 1 by js tau s. Okay, so this is what we have, and then second, again you can do Laplace for this. It will be s square phi s plus b by jp s phi s plus k by jp phi s equals to b by jp s theta s plus k by jp theta s. Okay, so these are two equations we have now, and we have to solve for, basically you can segregate for p's and thetas, but now you can write it in a matrix form basically, because what you can do is you can write something like this, where you have theta s phi s, right, as a vector equals to something, right, and then you can take an inverse of this, and you can solve for both phi s and theta s as a function of tau. So that's one approach to solve for them. Anybody has a question? How can I write it as a matrix form? No? Yes.
So you're saying that this is a function of tau s, so we're going to solve like that top equation has the tau s as last term. So we're going to solve that equation with that, or just in terms of
No. So what will happen is tau will appear in one of the equations here, right? So if you see, we have tau here and we don't have tau here. So, but yeah. So that's correct. So this will be 1 over j something, and this will be 0. So into tau or tau s. So again, same. It's showing the same steps that I did. So you can segregate them. And solve for. We going back to this equation, right? From here, I can solve for phi of s and then plug it in here, and then I will get a transfer function also, right? So in this case, what is happening? 5.4 is telling me that if theta s basically is an input, so the whole system can be divided as two transfer functions, right? One transfer function is like this, saying, so one transfer function is where input is tau, right? And we are getting out your theta. And one transfer function in this system, you get theta and you're getting phi of s out. So basically, a system can be broken you can make it as a cascaded system also. Like it's a multiplication of two transfer functions basically, right? So that's, so from here you can solve for phi of s, plug it in here, then you will get a ratio of just theta s to tau s. Okay? So we learned two things here, that your higher order, like system can also be represented as a multiplication of two transfer function, like two plants. So where input to this system is tau s, the output is theta s, and then theta s is the input to this system. So this is G1 and this is G2, right? So there are two transfer functions. Overall, if I'm talking about this situation here, right, where just a transfer function between this and this is a multiplication of G1 and G2, two transfer functions, okay? Questions here? So this is what I was telling you. What this you can write this as a matrix form, and so you have a 2 by 2 matrix here and this, and you can solve for this equation here. Okay. So basically, what will be phi s theta s? It will be theta s phi s equals to this matrix inverse, a 2 by 2 matrix inverse into 1 over js 0 tau of s. That's what you have to do, right? So when we invert that matrix and multiply this, we get two transfer functions or two quantities here. So these are the transfer functions there. Okay, and you will see that the characteristic equation, the denominator in both the cases is same. So that also tells you that poles for one system, doesn't matter which transfer function you're talking about, are same. That's why that's called the characteristic equation, that the poles for all the transfer functions are same, and you can exactly tell whether it is stable, not stable, or things like that. Okay, but there are two transfer functions, right? So two fourth order transfer functions. So if you see s square, when I say order, what do you mean by order? Anybody? That is the highest power of s in the denominator is the order of the transfer function. So that means how many poles will be there? 4 poles will be there. Okay. That's exactly. So now let's go a little further. So see if there are two transfer functions here. One transfer function is this, where we have phi theta s by ts, but you can also get a ratio for phi s versus theta s. So like you can say that in this situation theta s is considered as an input to the system. So if you see this thing is telling us, so we are saying, okay, why not find a ratio of this, and then that gives me a ratio of that. So that's like, if you see, it's a satellite subsystem where I give the torque, I get theta s, and theta s is an input to this. So you're basically, when you give a torque, theta s changes. But because of the spring coefficients, the solar panel also have some moments, right? So that means the solar panel is not moving directly because of the torque, but because theta was changing. That's why the solar panel moves. Okay? So basically, the combined transfer function from this to this is a multiplication of these two things. Okay? So that's one important kind of intuition here, that you can break down transfer functions as a, and you will see they will be very important when you are designing controllers for complicated system. You can first solve for theta s to give you a phi s, and then you can solve for that theta s for which you will need torque. So you can divide the problem and say, okay, I want my phi of s to be 0. What should be my theta s? Theta s, whatever input I get, and then, okay, this is the desired theta s, what should be my torque? So you can divide the problem and solve for theta s and phi s. Okay? Questions? Overall order, if you see, was 4th order, but now it's a 2 second order transfer functions. Okay. So the summary of transfer function concepts here Basically, a transfer function captures relationship between input and output, right? So that's clear, right? It captures the relationship. How we will use them will come later, but it captures a relationship between input and output. And use in Laplace domain or frequency domain. Transfer functions assumes that all initial conditions are set to 0. The roots of transfer functions, denominator polynomial are the poles, basically, and they govern the behavior of the system. The roots of the numerator polynomial are called zeros, and for multi-input, multi-output systems, there will be a matrix of transfer functions. As I said, there will be m into k transfer functions for each input-output pair. Okay, so that's important. And a higher order transfer function can be made up, represented as a cascade of 2 or more lower order transfer functions. You saw that in the last example. That So any questions here in this? Everybody okay? So the assignment that I will post today will consist of finding transfer functions for some problems. Okay. Before we use them to find transfer functions for several transfer functions for the UAV problem. Okay. Questions? No? Yes?
Is there a benefit besides just maybe like it makes more sense splitting it up and like decoupling it into multiple transfer functions versus just doing it all in one?
So yes, I think there is a big benefit because if you will also realize when we do the solution of the second order transfer function, it's much simpler and the solutions are close from, like you can tell when will the solution settle to the final value. What is the rise time? Okay, how much time it takes to go to the final value? How much error is there between the final value and the settled value? So all these questions can be easily answered for a second order transfer function. When you are finding the roots and everything, it's much easier. Try finding root for a nth order, right? So breaking down makes sense that, okay, I have n different systems. This system behaves in this way, this system behaves in this way, because first order and second order transfer functions, the analytical behavior is known to you. So now basically you're coupling them and say, okay, this behaves this way, this is stable, this is stable, this is stable, that means overall transfer function is stable. So that is the advantage of breaking down. Because we only can analyze lower order systems and tell you exactly what is happening. Yeah, good question. Anything else? Yes?
So are we evaluating things in the Laplace domain, or are we getting the relationship and then putting it back?
Yeah, so the system still remains in time domain, like your simulation, right? We are only analyzing things in the S domain and finding, based on that, finding in control inputs in time domain. But yeah, this is only for analysis purpose. Your system still stays in time domain. S functions are the transfer functions are mostly for analysis purpose. What is my system doing? And using that analysis to derive the controllers. Okay. So yeah, your input will still go in a time domain. So you can always, once you have solved and analyzed, you can always go back to the time domain. Okay. Yeah, that's always making this distinction that when we are analyzing versus what is the actual thing can always trick you up. So yeah, that's a great question. Anybody else? Okay, so let's move further. So now I want to show you if you have how to go from one form to another form, right? So let's say we already have a system into this form. So this equation you are all familiar with, right? Like this is nothing but if your system f of x is linear, you can write them in this form, or you can basically linearize it and write in this form, right? As a linear combination of states and linear combination of your inputs, right? And similarly, your output equation, which is y, can also be written as a linear combination of your states and linear combination of your inputs. So this is called state space form, right? So now the idea is, let's say a system is given. So earlier, like when we were doing Laplace, what were we doing? We were transforming your higher order differential equations to transfer functions, right? But let's say you already know a state space form and don't know the higher order equations, but you know the state space form. How do we go to transfer functions? So if state space form is given to you, how do we get a transfer function of that? Okay. So things are simple. Here also we can apply Laplace on both sides of both equations and basically solve for y and ratio of u. So this is where also you can show that if your initial conditions are not 0, your output will be a combination of response because of initial conditions and because of the input. Separate it out basically. So the idea is, okay, take Laplace on both sides of this equation. So as I said, but now when you are taking Laplace, this is a vector now, a vector of n states, right? So x of s is x1s to xns, or basically individual Laplace like this. So this is x1s, this is xns. So Laplace of individual state. And so basically it's a first order differential equation. So s into xs into a xs b us. So basically when we take Laplace on both sides, we get this equation in s domain. Okay. So now what we want to do is, because again the same problem, because correlated, right? If xs appears in both equations, u of s also appears in both equations. So we need to separate them out. So the one idea is, why not solve for x of s in the first equation and then substitute in the second equation, right? So what will happen in that case? So in that case, I can take x as this side, so it will be s. And this, remember, this is a scalar. S is a scalar value. So I can just multiply with identity matrix, right? So just doesn't change anything. Identity matrix into xs. What happens when you multiply a vector with identity matrix? You get the same vector, right? So basically, this is equal to writing x of s, right? So I'm not breaking any laws here, just because I want to take out x of s outside. It won't allow me because s is a scalar. So that's why minus a xs equals to bus, right? And now if you do this, if you take out xsi, remember what is I? Identity matrix of same size, like n into n, or if there are 3 states, it's 3 by 3. If I have 4 states, 4 by 4. Si minus a into xs equals to b u of s, right? Now I can solve for x of s from here, right? What is x? What will be that? So x of s will be si minus a inverse into b u of s, right? So now I have so that x of s you can substitute here now, right, in this equation. Okay, so when you do that, that equation becomes, if we go to the next page, so basically then you can substitute there. When you substitute, this is your new equation. Now it's just a function of u of s and y of s, right? So then you can find the ratio, and this ratio, the transfer function comes out to be this. So it is a function of both c, a, b, and d, right? So all a, b, c, d parameters. So a state space, if you remember, x dot equals to ax plus bu and y equals to cx plus du are represented by 4 parameters, right? What are those? A, B, C, D, those 4 matrices, right? And the transfer function now is a function of, so this is like a painful process. It will be inverting a n by n matrix, but that's the math. Okay. Any questions here? So you can go from state space to transfer function also, right? If state space is given to you, we have a transfer function. Again, this will be, how many transfer functions are there? Again, same, m into k. Your Y can be multiple inputs, multiple outputs, and UFS can be multiple inputs. So it will be a matrix of transfer function. For each input output, you will get a one transfer function. Okay? Questions here? Let's do an example from this equation was CSI minus A inverse BD. That's the equation that I have to just solve. Plug it in. Plug A, B, C, and D in there, right? So let's say a state space is given to me, right? Can somebody tell me what is A, B, C, and D here? Anybody? What is A here? Yeah. This is A, right? What is B? This is B. What is C? And what is D? 0, right? So that's it. Most of the real-time systems, D is 0. Like you don't have input directly going to the outputs. So now we have to find a transfer function, right, for this. So if you see my transfer, so we can do that. So what is transfer function? It is H of S is, or G of S is C Si minus A inverse B plus D is 0. But so that's the transfer function. C in Si minus A inverse B. So just start plugging things. That's all we have to do here, right? So first thing is, I think the most important part is this. Other things are just multiplication, right? So find your Si minus A. What is Si minus A? Si is S0, 0, S. That is Si. Minus A is just simply 0, minus 1, 4, 3. Oh, sorry, minus A. So it's just 0, 1, minus 4, minus 3. So that will be equal to S minus 1 plus 4, S plus 3. That's your Si minus A, right? Now you have to find inverse of it. So to find inverse, basically you will do is, we can find inverse here. How do you find an inverse of a 2 by 2 matrix? Anybody? Yeah, so 1 over determinant. What is the determinant? How do you find a determinant? AB minus BC. Guys, I will be literally I will be asking in midterm, find me a invert a 2 by 2 matrix. Find an eigenvalue of this matrix. Find eigenvector of this matrix. So I'm just repeating again and again because I'm hearing stories about undergrads. You guys complain a lot. Also, like people are saying if you don't tell them and they say, hey, they get a surprise, even though it was covered, they say, oh, we were surprised, we were not told that this will come in the exam. So I'm telling you again and again here, don't come and tell me you did not tell us, okay? So, okay. So if you find the determinant, it will be S into S plus 3, right? So this minus, so AB minus CD, so that will be minus 4 plus 4, right? So that's your determinant, delta S or something, whatever you call it. So the matrix A, Si minus A inverse will be 1 over S plus 3 plus 4 into adjoint of this, right? So I don't know if you know how to find adjoints, it will be, and people also say I skip step, but I cannot do a differentiation and show you and write here. Like, we will need a different class then. So adjoint means you skip this, you put this S plus 3, and then you skip this 4, minus 4, because when it's odd terms, you take a minus sign of that. So it will be plus 1 here and then remaining S here and take a transpose of it, right? So that will be what? When you take a transpose of this matrix, it will be 1 over S plus 3. And don't worry about grades. As I said, like I'm not teaching this class for grades. If anybody has an issue with grade, just come tell me what grade you want and I will give that grade to you. Yes. Okay. So if you're thinking where we are a great business, you just come to me. This is the grade I want. This is good for my future, my career. I will give that grade to you. Period. Simple. Okay. Let's solve it forever, right? No issues from grading issues here. Just come, tell me, I think I deserve this grade, and I'll give that grade to you. You have to at least ask that question to yourself, whether you deserve that grade or not, but you just, if you think you deserve it, I'll give it to you. Okay, it's on recording also, so I'll post it. So if we take the transpose of this matrix, it will be S plus 3, 1, minus 4, S, right? So this is the inverse of the matrix, SI A inverse of the matrix, right? So, which means S, if you just multiply things in, the matrix becomes 1 over S, right? S plus 3 cancels out. And 1 over S plus 3, and minus 4 over S plus 3, and S over, so S cancels out, so basically 1 over S plus 3. So that is your SI minus A inverse. So what is our transfer function? It is CSI minus A inverse into B. Right, so that's now you can multiply those two matrices. What is your C? C is 1, 0, right? So 1, 0 multiplied by this thing here, right? I don't want to write it again, so it's 1, 0 multiplied by, what is my B? B is 0, 2, right? 0, 2. So you just multiply these three matrices and you'll get the solution. So let's multiply. Today we'll do the steps. 1, 0.
I think you forgot the plus 4 on the denominator, where it's 1 over S times S plus 3 plus 4.
What, it's not here? Which one did I forget?
So up in the top right of your current screen, you have 1 over S times S plus 3 plus 4.
Wait, here?
Yeah, well for your CS, or just your SI minus A inverse, you have 1 over S times S plus 3 plus 4. And then when you go to the bottom, you no longer have the plus 4 on the denominator for the determinant.
Oh, yeah. Determinant. So yeah, I cannot cancel things then, right? Yeah. Good point. So if then we can factor it. So it will be S square plus 3S, S square plus 3S plus 4. So what will be the factor? It will be S plus 3, S plus 1. Is that correct? No. Yeah, that one. So I'm just saying that the sum should be 4 and then multiplication should be 3. No? What happens? Let's multiply and see. S square plus S square.
Plus 4S plus 3.
Oh, that will give me this? Yeah, so that's what I'm, let's multiply my thingy first. S plus 3, S plus 1 becomes what? S square plus 3S plus S, S square 3S plus S plus 3. Nah. See? I have answer in the next slide, but I wanted to find out.
Is there a chance that you forgot it? Because if it was S squared plus 3S minus 4, that would be easier.
What about, no. Let's just see the answer. Right now I'm blank here. So maybe it is not factorized, that's why they, let me check it out. It should be, maybe we should be able to write something, but is it fractions or? Let's keep it that way. Let's keep it that way for now. So basically, when you multiply this into this, you, because of the 0, this is what you get. So this is the transfer function of that x dot equals to ax plus bu, y equals to cx plus c. This is what you get. Because there was one output, one input, you got a single input, single output system. You get one transfer function out. Still thinking it was. Anyways, questions? No. We will not put it in state space. So state space was one form of the system, right? It mostly was used for simulating your stuff, right? Your state space was used to simulate the behavior. When your ODE, you were solving ODE, right? This will be used to designing the controller or analyzing the behavior of the system. You can keep things in S domain also, but you're not implementing this. You're not using it to simulate. It's just coming to the transfer function so that now I can tell you what will be the response of the system. Like it's easier to solve and analyze transfer functions. You can use so many tools. There are so many tools. Like when you go to feedback control next year with Tom Black, you'll see that there are so many tools like Nyquist plots, root locus, and your body plots. All those are tools developed for transfer functions. So you can use those tools to analyze and tell whether your system is stable or not stable, and to design controllers. Okay, I think we can stop here for today. How's the AUV assignment going on? The
Can you possibly post expected outputs for this one?
Yeah.
Because I have no idea.
Okay, I'll definitely do that. I think I showed the simulation you in the class, but I think it's a long time waited. But so for next 1 or 2 weeks, the assignments will be more mathematical, like finding transfer functions, and this might give you a break from method coding. Yeah, so the assignment 5.